We are now starting a technical session. We are going to present 4 papers. So let's start with the first one.
Hi, everyone. My name's Ellie Copps, and I was a SULI intern for Lawrence Berkeley National Laboratory in spring of 2021. And the paper that I'm presenting today is titled Analyzing Scientific Data Sharing Patterns for In-Network Data Caching. So over the past decades, data volume has been increasing exponentially in new scientific experiments and simulations. And this is particularly true for geographically distributed large collaborations, such as the Large Hadron Collider and Large Synoptic Survey Telescope. At the LHC in particular, annual data volumes are expected to increase by a factor of 30 between 2018 and 2028. And this increase in data volume also increases the network bandwidth requirements and time constraint data delivery requirements, which is part of why scientific collaborations are driven towards making data storage as dynamic and effective as possible. We've observed that a significant portion of the popular data set from these experiments can be transferred multiple times to different users as well as to the same user. And these redundant transfers can put an unnecessary strain on the network. So by using data sharing, we expect to reduce redundant transfers and save network traffic volumes. And we also expect to lower the average data access latency and improve overall application performance. So we are studying in-network data caching as a way to share data, in particular because these caches allow data to be stored and shared among users within the same region, regardless of their host institution. And this reduces those redundant transfers that we discussed earlier. So these types of caches are particularly relevant for the Energy Sciences Network, which is also called ESNet, because it buys transatlantic connectivity to bridge its US and European footprints. In-network caches can decrease bandwidth requirements on ESNet's transatlantic links, which can provide huge cost savings because subsea bandwidth is significantly more expensive than terrestrial capacity. In-network caches are also very useful for geographically distributed projects, such as those that exist in the high energy physics community. For example, the Large Hadron Collider is in Geneva, Switzerland, while Tier 1 sites for the ATLAS and Compact Muon Solenoid experiments are located overseas in the US. The goals of our study are to analyze cache utilization and network utilization for a regional data cache in Southern California. We also want to identify and study the effects of node downtimes because these downtimes can allow us to see the impact from adding or removing nodes in our regional cache. We also aim to predict future resource loads and the utilization of the cache so that we can increase data availability in the future as data volumes continue to grow. For example, we want to look at how an increased number of users will impact how effective the cache is, and we also want to study how many Xcache nodes will be needed in the future to maintain resource efficiency. In this experiment, we've been working mainly with data from the US Compact Muon Solenoid experiment, and this experiment is located at the Large Hadron Collider. It aims to crank up the performance in order to increase potential for discovery after 2025. And to do this, they will attempt to increase luminosity by a factor of 10. Luminosity is an important indicator of the performance of an accelerator because it's proportional to the number of collisions that occur in a given amount of time. So the higher the luminosity, the more data the experiments can gather that will allow them to observe these rare processes. And this is valuable, but it greatly increases the amount of data being generated, which is why the high energy physics community and other geographically distributed science collaborations can benefit from in-network caching. For this study, we've been looking at a regional cache in Southern California that consists of 14 federated storage caches and spans roughly 500 miles. And this is a pretty relevant distance from a research standpoint because caches of this size will be able to span major countries in the European Union as well as between major cities in the United States. Of the caching nodes in our regional cache, 11 are located at UCSD, 2 are located at Caltech, and 1 is located at ESNet in Sunnyvale, California. And what's notable about these disk capacities for the regional Xcache nodes is that the 2 at Caltech have around 7 times the disk capacity of the 11 at UCSD, which makes them interesting to study. The way that our regional cache works is that upon a user's request, there is a gateway redirector that will send the request to one of 14 Xcache nodes. If the request is a cache hit, meaning the data has already been stored in the regional cache, the client will get the data immediately. If not, the request is called a cache miss, and the file needs to be transferred from the data source to the regional cache. The study period for our full regional cache was between June and August of 2020, but we have data from ESNet from May through December of 2020. And all of our data analysis occurred on the Cori supercomputer at NERSC. So first we studied cache utilization, which has to do with the number of accesses on each node of the regional cache. And it lets us see how the overall number of accesses are spread between the 14 Xcache nodes. So to start, this is just a chart of summary statistics for the full regional cache. Here we have the data transfer size, which corresponds to the cache misses, and the shared data size, which corresponds to cache hits. And then on the right here, we have the percentage of the total data size that was shared. And we can see that this is increasing slightly over the summer and is around 65% on average. And its increase over time is a good indication that our cache is working and continuing to store more files as time goes on. On this slide, we're focusing on the total number of requests to the cache, which we are calling data accesses. The top plot shows the daily number of accesses, and it's broken down by which node completed the request, while the bottom plot shows the proportion of requests that each node completed. And we can see 2 times here in the study period where the entire regional cache went down for 1 day or more at a time. And a few times throughout the summer, a single cache would go down at a time, which we're going to look at a bit more later to study the impact of a single caching node. In particular, something that we looked at throughout the study was the 2 nodes at Caltech, which have 7 times the disk capacity of the other nodes. And these nodes in the plots are called XRD1 and XRD2, and they will always be the 2 blue ones at the bottom of the plots. We can see that towards the beginning of the study period, the Caltech nodes have around 1.5 times more accesses than the other nodes, but they drop down to around 1/3 as many from mid-July through early August. And all users can be directed to all nodes regardless of their physical location. So we know that this is not just due to where the users were located when they made their request. The difference here likely has more to do with the redirector policy than the 2 Caltech nodes themselves, but we can see that having a node with 7 times the capacity doesn't necessarily correspond to having 7 times the load placed on it. On top here, we have the daily number of cache misses, and on bottom is the daily number of cache hits. Just like with the accesses on the previous slide, they're divided by which node completed the request. And we can see again, looking at the 2 Caltech nodes, XRD1 and XRD2, that the hits and misses are higher than for the other nodes, but the nodes don't take 7 times the load of the smaller nodes as we might expect. Again, the smaller load on these nodes is likely due to an imperfect policy with the redirector, but it could suggest that having a larger disk capacity does not make a node more effective in the regional cache. Next, we have the proportional number of cache misses and cache hits for each node. And again, we can see some parts of the study period where a single node or the full cache went down. The non-Caltech nodes, which are numbered 0 through 10 here, and then the one at ESNet, are again taking mostly equal proportions of both cache hits and cache misses, but we can see that cache 5 has a very small proportion of accesses towards the end of July and the beginning of August here. And this is pretty inconsistent with what we'd expect, where each node has a roughly equal number of accesses, cache hits, and cache misses. So this might be due to a monitoring issue or some other reason that is currently beyond the scope of our study. On this plot, we can see the proportion of cache hits in blue versus cache misses in orange for each day. And the plot can tell us how well the regional cache is working to reduce the number of transfers. We see a slight upward trend throughout the summer, which is due to more files being stored in the regional cache that did not have to be transferred. And it's an indicator that our cache is working as expected. Overall, throughout the study period, our regional cache prevented 2.6 million transfers, and we are able to calculate the network demand frequency reduction rate, which is equal to the total number of accesses divided by the number of cache misses. And we found that this was equal to around 2.6. Next, we looked at how an increasing number of users in the regional cache would affect the number of accesses, cache hits, and cache misses. And in these two plots here, we took each number of users and took the average of all data points we had for the corresponding number of accesses. So on the left, we have the daily number of users versus the average number of accesses for that number of users. And on the right, we have the hourly number of users and hourly accesses. According to the linear model, which we have here, the accesses are roughly doubling with the hourly number of users, which does make sense with what we would expect. And we do see a strong linear relationship here. So next, using the same strategy of taking average values for a given number of hourly users, we plotted the average hourly transfers and the average hourly shares. And when looking at this data, we would expect, again, the number of shares and transfers to roughly double as the number of users doubles. We do see that this is roughly true for our data from the linear model. The transfers are slightly more than doubling on average as users double, and the number of shares are slightly less than doubling on average. Next, we plotted the data transfer sizes and data share sizes against the daily number of accesses. Rather than using averages like the previous plots, these are using actual data for daily accesses and daily share and transfer sites. And we can see that the shared data size is increasing a bit more rapidly with the number of accesses than the daily transfer size on the left here, which is what we would expect. And that's because there's a higher chance that more files will be cached as the number of users and accesses increases. We also, to isolate a single node, looked at statistics for only the node at ESNet, which we have data for between May and December of 2020. And the reason that we're isolating an individual node is to look at how it behaves as a part of the whole regional cache. We had a monitoring issue in late September through December where measurements were not collected, which you can see from the lower numbers of accesses in those months. But on average, through the study period, around 2/3 of data was shared from the ESNet cache rather than transferred from the source. On these plots, we have the number of daily data accesses, daily cache misses, and daily cache hits on the ESNet node through the study period. We see a large spike in cache misses at the end of October here, which we did look into. And we found that on October 26th, there were 15,000 transfer operations from just one user. Of these, around 3,300 have 0 file transfer size and 0 transfer time, which corresponds to a failed data transfer. And throughout our study, we are not taking into account these failed transfers, but for the other 11,763 transfer records, around 6,500 of these files were unique. In the future, identifying the exact cause of such a spike might allow us to adapt network policies and prevent these spikes from occurring. So that would help the cache function more efficiently. Here, going back to the ESNet node as a whole, we have a plot showing the proportion of files that were shared between 0 and 3,000 times. We can see that the highest proportion of files are shared fewer than 500 times. So next we zoomed in to just see files that were shared between 0 and 500 times. And we again see that the data is very focused on the left side of this graph, and most files are being shared fewer than 100 times. So looking into this even further, we have a histogram showing how many of the files were shared how many times. And we can see that most files are shared between 2 and 3 times from the ESNet cache. Finally, we have the outliers here showing that 3 files were shared 800, 1,000, and 3,200 times. Yeah, so on average, this chart is showing that unique files are shared from the ESNet cache around 2 times per day. And the file reuse rate is helpful because it's closely related to the network traffic savings, and it has to do with how many files are being shared from the cache each day that don't have to be transferred. Next, we studied network utilization, which relates to the volume of data accesses, transfers, and shares. And network utilization more directly relates to the network traffic savings because it has to do with the amount of data being transferred to and shared from the cache, rather than just the number of files. So here on top, we have the total transfer size each day in the cache, and on bottom, we have the total share size. And just a note, we switch back to looking at the full regional cache here. So we only have data from June through August of 2020. And overall, throughout the study period, we had 1.14 petabytes of data transfer and around 2.17 petabytes of data that was shared from the cache. These two plots show the transferred data sizes on top and the shared data sizes on bottom for each individual node. And what's interesting here is we can see that the nodes tend to follow each other with roughly equal values, although the Caltech nodes are a bit higher or lower in some places, even though they do still follow the same patterns as other nodes. And again, the difference in shared and transfer sizes for the Caltech nodes is probably due to the redirector policy. But overall here, we can see that nodes with the same capacity are, again, having roughly the same number and sizes of shares and transfers, which is expected and does give us some insight into the redirector policy. Similar to before, here we have the proportion of the sizes of transferred and shared data that was accessed from each node. And most nodes have a similar proportion of transfer and share sizes, while the two larger Caltech nodes can again take a larger or smaller proportion at times. In particular, we can see that the Caltech nodes have a higher transfer proportion than share proportion, which indicates that other nodes are more responsible for the network traffic savings in the regional cache as a whole. And we can also see again that cache 5 is taking a very small proportion of transfer size and especially share size on the bottom here, which is again inconsistent with the rest of our data and might be due to a monitoring issue for cache 5. So there's the cache 5 there. Next, this graph shows the proportion of shared data size versus transfer data size. And overall, through the study, our network traffic volume savings was around 2.17 petabytes, which again corresponds to that shared data size. And we calculated the network traffic demand reduction rate, which is equal to the total size of the data being accessed divided by the sum of the transfer size. And this was around 2.9, which means that roughly 2/3 of the total data size was shared from the cache. Next, we have the network demand reduction ratios for each node. And these graphs show slight changes in the ratios over time. On top here, the network demand frequency reduction ratio is, again, the total number of accesses divided by the total number of transfers. And we can see that this stays around 2.5 for most nodes, but there's a large spike towards the beginning of August. At the bottom, we have the traffic volume demand, which again refers to the total data access size divided by the transfer size. And it does have a bit more variation than the frequency reduction ratio, which makes sense because each access does not have a set file size. So we expect the data sizes to vary more by chance. Looking at the peaks in August here, we can see that the frequency demand reduction peaks at almost 35 for some nodes, while the traffic demand reduction peaks at around 14. Next, we will look at the reduction rates for the overall regional cache, and we can see that the transfer frequency demand spikes in August, but only up to a reduction ratio of around 12. And as we saw on the last slide, individual nodes went up to almost 35, which shows that the spike was probably more due to a few nodes rather than to the cache as a whole. And we can see a similar occurrence on the bottom plot here with the volume demand. And finally, we studied the impact of a single node on the cache by looking at times that single nodes went down and seeing what happened in the rest of the cache at those times. So in looking at these downtimes, we isolated all times where a node was down over a full hour or longer. And in these times, we would expect that there would be a higher number of transfers and a lower number of shares in the regional cache as a whole, because taking a node out of the network effectively reduces the number of files that have been cached. And we observed that when a node went down, the remaining nodes tended to proportionally split the load that had been on that downed node. And this was particularly true for access proportions. We found that the ESNet node, likely because it has a slightly larger disk capacity than the other nodes, tended to take a bit more of the access load than other nodes. And when looking at the two larger nodes at Caltech, the XRD1 and XRD2 nodes, we found that they didn't really act as expected compared to the other downtimes. And because of this, when we show the average changes after downtimes on the next few slides, we split them into two categories. And one does include the Caltech data and one does not, just to show what it looks like without these two nodes. So here we have histograms for the change in accesses from before to during a node downtime. And the blue bars here show the change in transfers between the time before and after the downtime, and the orange shows the change in shares. On the x-axis here, we show how the number of nodes that had been down before affected the change in accesses. And we didn't find a very strong correlation between the number of nodes down and the change in accesses because we studied a total of only 7 separate downtimes. So we would need more data to see a correlation between these numbers of nodes and how the accesses are changing. But looking at the total plots here, we can see that the transfers tended to increase slightly on average, while the shares tended to decrease slightly on average, which is in line with what we would expect. Next, we have similar plots here using the transfer size and share size rather than the number of transfers and shares. And again, we can see that the transfer size tends to increase slightly on average, while the share size decreases slightly on average. And more data would help us to make some better conclusions about the impact of these node downtimes. But using all of our data, we were able to make some estimations regarding future loads on the cache. We predict that as the number of users double, the number of accesses will double, and the number of transfers and shares will also roughly double. And we also can predict that as users double, the share size will more than double and the transfer size will less than double because more files are being stored into the cache as there are a higher number of accesses. From studying the node downtimes, we can predict that adding a node will evenly take loads off from other nodes, and there will be a higher proportion of data being shared from the cache as the number of accesses and the number of nodes increases. Adding a node can also reduce data latency or the time it takes to access files on average because more files will be readily available in the cache and don't have to be transferred. And from looking at the Caltech nodes in particular, we can predict that adding a larger node might not necessarily take a proportionally larger load off of the network, but it does hold more files, so that could cause an increase in traffic reduction rate over time. It would be valuable to assess redirector policy in the future to take full advantage of these larger caching nodes. To summarize, we have studied a regional cache as a shared data caching mechanism, and we've looked at how to distribute an Xcache system to reduce network traffic and increase data availability for geographically distributed scientific collaborations. Over the study period, our cache saved 2.6 million transfers and around 2.17 petabytes of data transfer in total, which corresponded to a network traffic reduction of nearly 3. It also reduced the transfer frequency demand by a factor of 2.62. We did see that the proportion of shared data accesses increased with time, which will decrease application wait times and network loads. In the future, adding additional nodes will allow more data to be cached, which again will allow networks to maintain data availability and to cope with increased demand. Further studies might include looking at how repeated cache misses affect performance, as well as anomalies, particularly the spikes in the traffic reduction ratio. If we can understand these spikes, it'll help us to understand if the cache is working well and saving traffic as expected. And finally, we would like to acknowledge the following researchers at Caltech, UCSD, and ESNet, as well as the US Department of Energy, the National Science Foundation, and the National Energy Research Scientific Computing Center.
Are there any questions? I see one question. The files are read-only or can also be modified, can also be written?
Files are more like read-only.
Mostly read-only.
Yeah,
okay.
Because the files cannot go back to the original.
Okay, thank you very much. We can now proceed. Let me see if we can go back to our first paper, Evaluations of Network Performance Enhancement on Cloud Native Network Function. And this paper should be presented by Yong-Xuan Huang.
Hello everyone, and welcome to my presentation. Let me start by saying just a few words about my own background. I'm a PhD student of National Tsinghua University in Taiwan. My advisor is Jerry Chou. Our research are related to network function virtualization. As you can see on the screen, our topic today is evaluations of network performance enhancement on cloud native network function. We thought it would be useful to divide our talk into 4 main sections. I would like to introduce our motivation first, and then explain our method design and experiments. Finally, we give a conclusion based on our experiment results. Suppose you are a cloud service provider and increasing 30% of the customers in just 1 week. How would you make your network infrastructure flexible enough to respond to this situation? NFV may be the answer. NFV stands for Network Function Virtualization, which replaces dedicated hardware with software instance that can be deployed, scaled, and migrated dynamically. NFV allows providers to run network function instance across different servers or move them around as needed when demand changes. For example, if a customer requests a new network function, they can turn on a new VM to handle that request. If the function is no longer needed, the VM can be destroyed. This can also be a low-risk way to test the value of potential new service. The core of network function is performing packet processing. Migrating network functions means implementing the same flow of processing packets onto a different platform. When we are going to virtualize a new network function, we first abstract the network function from particular hardware and based on its feature and performance criteria, choose the proper virtualization platform, then implement the procedure with the same logic on the platform. This is what we call VNF, a virtualized network function. We can operate this VNF individually or embed the VNF into an orchestration manager. Although NFV introduced substantial benefits, it is still challenging to put the deployment of software-based network functions into practice. One of the major obstacles is the difficulty in achieving high performance comparable to hardware-based when running software network functions in a virtualized environment. Hence, recent researchers focus on various acceleration techniques for VNF that address these performance issues at different levels. Furthermore, acceleration techniques can be specialized in particular aspects of the processing pipeline and therefore improve the performance regarding resources such as compute, memory, or storage. But before we get into the acceleration techniques, I would like to look at this in a bit more detail. What are the root causes making software network performance deficient? The first root cause could be Linux packet processing. We can divide the packet flow into 3 stages. Stage 1, packet is transferred from network interface card to ring buffer. Stage 2, packet is transferred from ring buffer to a socket receive buffer. Stage 3, packet data is finally copied from the socket's receive buffer to user space by data receiving process through socket-related receive system calls. Here could be the root cause, because the packet needs to copy from kernel space to user space, which costs more time and causes the delay. The second root cause could be the overlay network. Why do we need overlay network in virtualized network environment? In traditional network, all the instances need IP, and the IP should be routable. However, if we have increased 100 times network scale, our routing table are not able to afford it because the routing table is limited. Using overlay network to divide the whole network into small layer 2 network is a practical solution. However, this means every packet on both the sender or the receiver side traverses the Linux network stack twice and also in a virtual switch, which also causes the delay. In order to resolve these issues, let us take a look at existing network acceleration solutions. This includes software-based approaches that optimize packet processing through the software network state after receiving the network interface card, as well as approaches that offload parts of the processing pipeline to programmable hardware. A common practice is to offload network function processing from the host to hardware. Then network functions can perform much faster when they executed on a general-purpose CPU. Available methods are employing popular hardware such as NPU, GPU, FPGA, and SmartNICs for NFV acceleration. Software acceleration is also often used to enable high performance for compute-intensive network functions. Packet processing such as encryption and transcoding, which require significant CPU resources and involve complex CPU calculation. It is worth mentioning that most of the software acceleration functions in user space, because it is easier to modify and implement a new algorithm. We have seen the NFV concepts and how to accelerate the network function in practice. Also, VNF are widely used in NFV currently. They still have limitations as digital service providers move toward delivering more agile services. In the initial transition from physical elements to VNF, vendors often lifted embedded software systems entirely from appliances and created one large VM. However, without attempting to optimize these VMs, they created efficient, single-purpose virtual appliances that were still hard to manage and maintain. And VM has issues with slow provision time or CPU and memory overhead. So here comes the container. Containers allow users to package with all of the files necessary to run it while sharing access to the operation system and other servers resources. This approach makes it easy to move the content component among environments. As an evolution from VNF, cloud-native network functions are designed and implemented to run inside containers. The containerization of network architecture components makes it possible to run a variety of services on the same cluster and more easily on board. But the acceleration requirements are still remain. So how the existing packet processing solutions performs on container-based network function. So we have three contributions in our research. The first is to describe existing packet processing framework using in NFV with container. The second one is to evaluate the performance network performance after packet processing framework applied in NFV with container. The third one is to discuss and tuning the packet processing performance impacting by network architecture. Here, we are going to deep dive our methods. We use Kubernetes to be our evaluation platform since Kubernetes is a very mature container manager. Kubernetes does not provide any solution for handling containers networking. It offloads networking to third-party certificated plugins called CNI plugins. Most CNI plugins use overlay. We already know that it is easier to design a new algorithm if the packets are processing in the user space. The existing user space acceleration solutions includes FDIO VPP and DPDK. FDIO VPP use vector to process packets instead of sequential processing. We can regard this solution as a lockless parallelism. Contif is a Kubernetes network plugin that uses FDIO VPP with DPDK as the data plane for packet forwarding between parts in the Kubernetes. As the architecture shown, DPDK is used in packet switching, and VPP is used in packet processing. Normally, the Linux kernel has always been an ideal place to implement monitoring, networking, and security. Unfortunately, this was often impractical as it required changing kernel source code or loading kernel modules, and resulted in layers of abstractions stacked on top of each other. eBPF is a kernel feature that can run sandboxed programs in the Linux kernel without changing kernel source code or loading kernel modules. By making the Linux kernel programmable, infrastructure software can leverage existing layers, making them more intelligent and feature-rich without continuing to add additional layers of complexity to the system or compromising execution efficiency and safety. Cilium is another Kubernetes CNI plugin. The foundation of Cilium is eBPF. Because eBPF runs inside the Linux kernel, Cilium modules can apply and update it without any changes to the application code or container configuration. It is possible to use routing instead of overlay network since the routing module has been updated. We built a simple table to compare these different solutions. In our experiment setup, our goal of the experiments is packet processing. So we do all the experiments in one host in order to reduce the side effect of network equipment. We first estimate the baseline of host and VM, then compare the solutions along with the network models individually. In our testbed, we use KVM to be our VM baseline and the Calico to be our Kubernetes CNI baseline. In our results, we found that kernel space acceleration can help to reach nearline in host, but user space acceleration is the worst. The performance on VMs is quite different as we thought. All performance decreasing on VM, even CDM is worse than container baseline. Using VM to isolate CNF is a practical use case. So we have noticed that the existing acceleration solutions are not function in a non-tuning VM. We try to increase our VM's performance. So we use SILV, and we found that both VM and container baseline has increased, but the trend is still the same. Since the container baseline has increased, CDM still can't reach container baseline, but better than Calico eBPF mode like host. We wonder why the kernel space acceleration solutions cannot reach the baseline. So we found that the MTU size impact significantly on network. The performance can sometimes increase after adjusting the MTU size. Due to eBPF programmable in kernel, packet processing benefits from using native routing instead of overlay network. So after using native network, kernel space acceleration can get the best performance. Kubernetes CNI with the user space and the kernel space seriously impact the CNF packet processing performance. Kernel space acceleration on the host or on the VM after tuning can get the best performance result. User space acceleration looks not helping in container packet processing even with hardware support. In the future, we could perform more comparisons of network features on container like security or IPVM management for further research. Thanks for your listening.
Okay, thank you very much for the presentation. Are there any questions? So if not, I have a question for you. So it looks like that right now user space is not enough for achieving a reasonable level of performance. How many years do you think will be required before the next processors will be able to catch up and deliver the required level of performance?
I think the network acceleration in kernel space should maybe the main solution in the future in the recent years, because I think it is it's more easy to more efficient to help the performance network performance increase. For example, even the Google or some cloud providers, they are offering the kernel space accelerations to be their main solutions.
Okay, thank you very much. So we can now proceed with our next paper, a hybrid virtual network function placement strategy for maximizing the profit of network service deployment over dynamic workload. And I guess this paper is going to be presented by Chi-Chen Yang.
I am Chi-Chen Yang, a master student from National Tsinghua University. Professor Chou is my advisor. The title of paper I will present is a hybrid virtual network function placement strategy for maximizing the profit of network service deployment over dynamic workload. This is our outline. First, talk about our motivation and objectives, then explain our approach and see the experimental evaluation. Finally, is our conclusion. Network function virtualization has become a promising technology recently. Traditional network functions such as firewalls and load balancers are mostly implemented by hardware. NFV technology separates network functions from hardware device, implements them in a software-based manner. Thus, virtual network functions can be containerized and hosted on commodity servers. So it not only greatly increases the flexibility of deployment and maintenance, but also reduces the cost of infrastructure construction. One of the key challenges of the network function virtualization orchestration is the virtual network function placement. We consider the problem from the network operator's point of view, with many requests of network service must be served. A network service is composed of a service function chain. To process service function chain requests, network operators have to initiate virtual network functions to host network functions on physical machines. The placement problem is based on the objective to decide the placement of VNF, the mapping of NF, the routing of SFC, and accept or reject SFCRs. The common objectives are as follows: maximize service providers' revenue, minimize service operation costs, minimize reconfiguration costs. A valid placement must be subject to many constraints, including the limited computing capacity on physical nodes, bandwidth on network links, and the service quality requirements. Here is an example of placement. There are two service function chain requests and the network topology. Service function chain requests have different demand value. The resources required by each NF are indicated in parentheses and are proportional to the traffic demand of the service function chain request. The resource capacity of network topology is mentioned in the picture. Here are two possible placement results, placement A and placement B. The difference between them is that there are more VNFs deployed in placement B. We consider the multi-tenancy, so the same type of an NF from different service function chain requests can be served by a single VNF. If a VNF is launched, there is a resource consumption to maintain it, called basic resource consumption. Thus, we can see that placement B has more resource consumption in total, but with lower latency for service function chain request too. So, how to maximize the service quality and minimize the resource consumption cost is important to the network operators. The other challenge of the placement is that the traffic demand of network service is dynamic. So the placement should be adjusted. For the computing resource, we leverage idle resource in physical machine, but if the resource capacity of the physical machine is insufficient, we deploy a new VNF and then migrate. However, deploying a new VNF causes service delay because it needs several initialization steps. In the case of insufficient bandwidth resource, we should reroute the traffic. This is an example of dynamic traffic. The left part is the placement at time t, the right part is the placement at the next time interval. We leverage idle resource in the physical machine. However, a violation occurs on PM4 due to insufficient computing resource. Therefore, how to reconfigure the placement to minimize the service delay penalty from service deployment reconfiguration is a challenge for network operators. We can see that the VNF placement problem faces many challenges. Now we discuss the existing approaches. One is to formulate the VNF placement problem as ILP problems. Then using ILP solver can find the optimal placement. However, solving VNF placement is an NP-complete problem. So it is time-consuming, especially for larger problem size or dynamic workload. Thus, many greedy algorithms have been proposed to quickly obtain approximated placement results. In the end, neither of them can make quick and accurate placement decisions at the same time. In this work, we propose to combine the two approaches to obtain their benefits. However, we have several challenges: when and how to use the ILP and greedy algorithms, how to solve the time-consuming problem of ILP, and how to solve the problem of dynamic traffic. Then I'm going to describe our methodology. There are some key points of our hybrid design. First, to solve the time-consuming problem of ILP, we reduce the problem size of ILP by classifying SFCRs into stable and unstable ones, according to their workload variation over time. Second, we let ILP determine the placement of stable SFCR. The intuition is that stable SFCR are with a heavier workload and the number of the stable SFCR is less. So we can use ILP to obtain the maximum profit from them. Third, we let greedy determine the placement of unstable SFCR. The intuition is that unstable SFCR are more likely to be migrated over time due to traffic variation. But last, we place stable SFCR first to avoid resource fragmentation because they with heavier workload need more resources. We analyze the real workload on 4 real topology. In the figure, each dot represents the traffic between the nodes. The x-axis is the mean of the traffic, and the y-axis is the relative standard deviation. We found that the traffic with a heavier workload has a lower relative standard deviation, and the traffic with a higher relative standard deviation has a lighter workload. Thus, we can conclude that the traffic with a heavier workload is stable. Moreover, we also found that most of the traffic has a small workload, and only a few traffic has a large workload. The whole workflow of our hybrid approach is as follows. At the first time interval, we use the ILP solver to determine the optimal placement of stable SFCR. And then we use a greedy placement algorithm to place the unstable SFCR. At the remaining time interval, we propose a greedy reconfiguration algorithm to resolve the violation due to dynamic traffic demand. Thus, our hybrid approach can make quick and accurate placement decisions. First, we explain the problem formulation of ILP placement strategy. Because through ILP, we can get the optimal placement results. The objective of our problem is to find the best BNF placement at each time interval, so that the net profit can be maximized. Servicing SFCR receives revenue, while deploying SFCR results in costs, including resource consumption costs, service deployment costs, and the reconfiguration costs. Most of the network services are latency sensitive. Hence, the revenue of a SFCR is strongly correlated to its end-to-end delay. Moreover, the revenue of SFCR is proportional to the amount of the traffic. SFCR can be rejected, so the revenue only comes from the accepted SFCR. The operation cost of a network operator is often proportional to the resource consumption from servers and network equipment for serving the traffic of SFCR. The CPU consumption of a VNF consists of 2 parts. The first part is the workload-dependent resource consumption. The second part is a basic resource consumption. The bandwidth utilization is proportional to the bandwidth consumption cost. Moreover, we define the penalty cost associated with deploying a new VNF and redirect the traffic of SFCR, because this operation will cause service interruption and delay to the SFCR. There are some constraints below. We have resource constraint due to the limited computing resource and bandwidth resource. The second constraint is the NF mapping constraint. Each network function only can map on one physical machine. The last constraint is the traffic constraint. We ensure incoming traffic is equal to outgoing traffic, and the traffic cannot be split. We use an example to illustrate the algorithm. We assume 2 SFCRs need to be served, and SFCR1 is stable. At the first time interval, we use ILP solver for stable SFCR to get the optimal placement. Now we present our greedy placement algorithm for unstable SFCR. We follow the 3 principles to design our algorithm. First, SFCR with higher traffic is with higher priority. Second, we will use the deployed BNF to run our greedy placement algorithm to place the remaining unstable SFCR following step 1. So our target is to place SFCR2. Then following step 2, we deploy a new VNFE and map NFE on PM4. After mapping NFE, we'll try to map NFA following step 3. We will use the BNFA and map PM1 to set the basic resource consumption and the deployment cost. Then step 4 is to decide the routing from NFA to NFE. We route the traffic through the shortest path from PM1 to PM4 to minimize the end-to-end delay. The shortest path is highlighted in purple. For the remaining NF in SFCR2, we repeat step 3 and step 4 until they are all mapped. So this is our placement result at the first time interval. Finally, we describe our graded reconfiguration algorithm for resolving resource violation. This is an example of a violation on a node due to dynamic traffic. We can see that the traffic demand increases. There is a violation on PN1. To solve the violation, we follow step 1 to find the NFV in SFCR2 to be migrated. Then we follow step 2 to find the shortest path between the predecessor and the successor. The shortest path is highlighted in green. Then we follow step 3. We deploy a new VNFD on PN3 and migrate. We also give an example to illustrate the reconfiguration algorithm when a violation occurs on the link. We assume the bandwidth capacity of the topology is as in the picture. So there is a violation on a link between PN1 and PN3. Following step 1, we find the SFCR2 as a redirect target. Then following step 2, we find NFD and NFA. Then following step 3, we find the reroute path that is highlighted in green. Then we see the experimental evaluation of our hybrid approach. Our comparison method is called ILP static. It uses the ILP solver to decide the initial placement of all SFCR and fix the decision across all time intervals. The experiment is to show the comparison of computation time. We can see at the first time interval, ILP static costs much more time than hybrid because our approach only applies ILP on stable SFCR. For the remaining time interval, our approach only uses greedy, and its time is significantly lower than ILP. Therefore, our approach can always make timing decisions, and greater improvement can be expected when consider larger networks and more SFCR in the problem. Next, the experiment is to compare the profit. At the first time interval, although our hybrid approach only uses ILP for the stable SFCR, it can still achieve a similar result as ILP static. For the remaining time interval, our approach can get even higher profit than ILP static, because ILP static starts to reject SFCR due to time variant workload. However, our hybrid applies reconfiguration to resolve violation. Therefore, we can have up to 45% profit improvement at one time interval, and the 24% improvement can across all time intervals. In conclusion, we propose a hybrid VNF placement approach to maximize the net profit of a network service provider. We overcome the time complexity problem of ILP and resolve the resource violation caused by time variant workload. The experiment results shows that a hybrid method can make quick and accurate decisions. Thank you for your listening.
Okay, thank you very much for your presentation. Are there any questions for our speaker? So, okay. One question for you. So, it looks like you are using the time-consuming ILP solver with reduced size. So you are not solving the full problem, but just a scaled down version. Did you compare results by using only the greedy algorithm? Because even though you are not solving the full problem, you are still using so much time, as shown by one of your latest slides. So the ILP solver is still using so much time, even with a reduced problem. Since you are then, you then get anyway a suboptimal results. Did you try comparing results only with the greedy approach or some other approximated approach?
I didn't compare with greedy, but I think because the traffic in the backbone network, they are we follow the 80 and 20 rule. So the 80%, so 20% traffic is stable, and then the workload is higher. So we think the for ILP we just care the 20% request and can get the more higher result, higher profit from ILP, from the method.
Okay, thank you. Thank you very much. So we can now proceed with our last paper. So we do have one final paper, which is called Characterizing Resource Heterogeneity in Edge Devices for Deep Learning Inferences. Is there any of the author presenting the paper?
Yes, it's Piyush. Yeah.
Hi, thank you. So please go on and share your screen.
I hope you can see the screen.
Yeah,
All
sure.
right.
Thank you.
Thank you, Massimo. Hi, my name is Piyush Subedi. My colleague Jianwei Hao and I, under the guidance of Dr. Inki Kim and Professor Dr. Inki Kim and Professor Dr. Lakshmesh Ramaswamy at University of Georgia, have been working on characterizing resource heterogeneity in edge devices for deep learning inferences, which happens to be the title of this workshop paper as well as the presentation. The agenda of this presentation is as such, which also mimics the outline of the paper actually. We begin with the problem statement or the motivation behind the study. Then we briefly discuss some of the related works in this area. Then we also explain the evaluation setup that we went for. And then we finally discuss the experiments and the results and also some of the findings or insights from our experiments, and finally conclude and explain some of our future work. So to briefly cover what edge computing is, we have these two extremes. One end, we have these end devices which are very close to us, our laptops, our desktops, our day-to-day mobile phones, or day-to-day daily use commodities. They are good enough, but then good enough for day-to-day tasks, but then there are some tasks that are computationally challenging, resource intensive, maybe even memory storage intensive. So for those cases, our devices are just not feasible enough, which is why cloud computing has become so popular over the past decade or so, where we can delegate these challenge or difficult tasks or computationally challenging tasks to a server or a much powerful server or a server farm, or even use it as data centers. But again, as we can see, the problem with that is we have to send the entire request to the cloud, and then the cloud has to send the response back, which means there is a bit of a latency there involved, and also establishing and even maintaining these farms or these clouds is an expensive operation. So to mitigate these issues, we have this paradigm called edge computing, which lies somewhere in the middle between these two extremes, where edge devices are closer to the end devices, provide slightly higher, significantly higher, in fact, in some cases, significantly higher computational capabilities, while also being cost and energy efficient. We also have cloud edge hybrids, where if the task is not feasible enough for the edge, we can delegate it to the cloud. So sticking to this realm, we want to evaluate how feasible are these edge devices at performing some machine learning, which has been, again, very popular these days in the field of computer science, machine learning or AI tasks at the edge. How feasible is it? Specifically, so given that we'll focus on deep learning tasks, which is, again, one of the more famous machine learning algorithms in use these days. So given that there are these wide variety of deep neural net architectures, and these very heterogeneous edge devices from different vendors, which model device combination would be ideal or most feasible or most suitable for DL task at the edge? Along with that, we also want to evaluate which machine learning framework. Again, there are a plethora of these frameworks, which machine learning framework would be ideal at the edge. We also try to answer the question, how well is batched inferencing supported at the edge, or how does it affect the overall performance of machine learning models, specifically deep learning models at the edge. Some of the works in this area, some preliminary studies that precede our work have been shown on the screen here. So basically, there are studies that focus on characterizing the frameworks, some that want to see which models fare better, some that want to see which devices, given a framework, given a model, which device looks better. But our study is more comprehensive in that we want to see, given a decent set of frameworks, decent set of models, given a decent set of devices, what would be a good combination. So our work is more comprehensive than the works that have been outlined. And also, we also look into, like I've already said, we also look into batch inferencing. So the evaluation setup is as such. The devices that we cover are, on the left-hand side, you'll notice the devices that are cheaper and more, slightly less powerful than the ones on the right, because the right ones have powerful GPUs, powerful CPUs, and are all from NVIDIA's. Basically, we have the Jetson Nano, TX2, and the Xavier NX in that increasing order of processing capabilities. We do have GPU for ordered N2, but then leveraging these GPUs using the frameworks, machine learning frameworks, which predominantly have been using NVIDIA's parallel computing platform and toolkit called CUDA. It was beyond the scope of this project having to build the framework to support these CPUs. So we could not leverage the GPU for ordered N2. So on the left, we have CPU-based inferencing, devices that we use for CPU-based inferencing. And on the right, we have GPU-based devices. The frameworks that we chose are the most stable ones, most actively worked on, and one of the most popular ones. We have Apache's MXNet, Google's TensorFlow, and Facebook's PyTorch. The models that we have used are as such. We have AlexNet and SqueezeNet, which are lightweight in the sense that the number of floating point operations is significantly less compared to other models. Then we have ResNet 18 and ResNet 50, which are average size models with decent number of floating point operations involved. And finally, we have these heavy models like DenseNet and VGG16, which have, as you can see, great number of layers and higher number of floating point operations involved. So that makes the set of models very representative of all the image classification models so far. So yes, something that I should mention is we looked into the image classification models only. So the whole benchmarking process is, or the characterization process is as such. We have a bash script that takes in as to how many iterations are to be run per experiment. Generally, the minimum that we went for was 10 to ensure that there was a statistically confident, we have statistically confident results. Along with other parameters like what batch size to use, number of batches, number of warm-ups, which model to run using which framework, and using all these configurable parameters, the bash script invokes a Python script, which is actually the benchmarking script. And the sole reason behind having a bash script to invoke a Python script is with each successive iteration, we wanted to ensure that the Python runtime opens up and then closes off, which ensures that all the cache that was used by the runtime has been invalidated. Then on the benchmarking side, we start with preparing a data loader, which is framework specific. The data loader prepares the input images for the models to feed into the models. So the images that we use for inferencing were all used from ImageNet 2012 validation data set. Then the next step is loading and configuring the model into the memory. By configuring, we mean CPU or GPU. The model is supposed to use a GPU or CPU and all those stuff. Then finally, we spin off a background thread that is essentially supposed to capture the system statistics like CPU usage or power usage or disk usage or memory usage. And we use Linux-based utilities, popular utilities like systat and JTOP. JTOP is for primarily for NVIDIA devices. So all these utilities are started in the background, and simultaneously, well, almost simultaneously, we run the model. And once the model is run for a sufficient number of batches, we stop the execution, and all the statistics are then parsed and stored in the disk. So that completes one iteration of a benchmark, and we repeat the same process for a different set of configurations. So finally, to discuss the results and some of our findings, the first experiment was a simple one where we ran these models using all the frameworks on all the devices. However, the result that we are seeing right now is just for PyTorch, because that was the best performing framework amongst the three, which is one interesting finding, I guess. Some obvious or expected results where AlexNet and SqueezeNet are definitely faster. The left-hand side, the left y-axis denotes the average throughput or number of inferences made per second. And in that case, in that sense, we have AlexNet and SqueezeNet, and even ResNet'18, which is fairly high compared to other heavy-duty models like DenseNet and VGG16. Another thing to note is even for batch size of 1, primarily due to its powerful CPU, GPU-based devices like Xavier and NX and TX2 are significantly better than the other devices, particularly if you compare it with CPU or based devices like Odroid and Raspberry Pi. It's quite significantly better. The red line that you see corresponds to the average accuracy of these models. And if we are looking for a model that has good enough throughput with good enough accuracy, then it looks like ResNet'18 is a good choice. The second set of experiment involved using different batch sizes, and we just showed the results from AlexNet here. So we use batch sizes in the order of 2, which is the way to go for using GPUs, to leverage GPUs prowess in parallel computing. So all the frameworks showed good results in terms of batch size, increasing batch size. There's as much as 2 times, so it's maybe even higher gain in throughput with increasing batch size. MXNet could be said that it uses GPU better because the results are slightly better than the other 2 frameworks. We do not expect CPU-based devices to perform any better with increasing batch size, which is the case, while GPU-based devices, thanks to their GPUs, which are very good at parallelizing inferencing, they show quite considerable improvement. And it should be noted that we cannot just keep on increasing batch size because, again, these are edge devices with limited storage capacity. So we start running out of memory once we start dealing with higher and higher batch sizes. So there is a limit there. In terms of resource utilization, to point out some of the obvious or the expected results, yes, heavyweight models like Dense and VGG16, they use CPU or memory and power a lot compared to the other devices. Something to note would be PyTorch seems to be the most memory efficient. If you look at the graph in B, while MXNet seems to be doing good in terms of CPU utilization and power usage overall. So yeah, that's another insight. So far, we have only discussed the throughput as the inference time, the total time taken to infer, which doesn't count how long it takes to actually load the model into the memory. So this is something that we wanted to evaluate because all the frameworks have take different amount of time to actually fire up the model and start inferencing. In that respect, TensorFlow, as you can see, is quite poor when you compare it with other models, while PyTorch seems very, very good. Again, the green part, which is actually the inference time, is actually the inference time taken to perform 30 inferences. So if you consider just one inference per second, then if one inference, then the time is even lesser. So load time is quite significant, quite high compared to the inference time. Finally, something that we wanted to come up with, just to have an idea of what combination would be good. So so the y-axis is the average throughput, the x-axis is the price of the device in dollars, while the size of the bubble that you see is the power consumption. These are the three things that are generally the critical factors when selecting, when performing deep learning at the edge. So if you're looking for something with high throughput and don't really care about the cost or the power consumption, then of course Jetson TX2 and Jetson Xavier would be a good choice. But then if price is a concern or even power is a concern, then Jetson Nano or maybe even Raspberry Pi, if throughput is not that big of a concern, then maybe even consider Raspberry Pi. Something missing here is the Odroid N2's results, because the power measurements that we got from Odroid N2 using our own power measurement circuit wasn't very reliable. So we opted to discard it and maybe in the future have a more stable result for that. Finally, to conclude the whole study, it's our preliminary study, which was to see which hardware model and software combination in terms of framework would be a good choice at the edge. So hardware, the type of hardware, if you have a GPU, you tend to have better performance. Again, batch size also has great impact on throughput, particularly, in fact, only if you are using a GPU. And in terms of framework, we claim that from our preliminary study, we claim that PyTorch looks like the most efficient system framework in terms of both throughput and system utilization. Something we opted out of was framework-specific optimizations, and the reason we did not include them is basically because we wanted to provide a common ground for all the frameworks. So maybe in future, which is one of our future works, is apply those framework-specific optimizations and see how high can we get the throughput, overall throughput. Another thing that we could investigate on is using tensor processing units, which are specialized hardware units, designed particularly for AI inferencing, like Google's Coral USB accelerator, Intel's Neural Compute Stick, and see how they fare among the other devices. We also would like to evaluate if multi-tenancy is something that works at the edge, and which is something that we are working on as well. So yeah, so this has been a brief presentation on the paper that we submitted to the workshop. If you have any questions, please feel free to come up. Thank you.
Okay, thank you very much. Any question for our speaker?
I have a question.
Yeah, please
okay,
go.
Yeah, thank you for the very much interesting presentation. You compared MXNet, PyTorch, and TensorFlow using AlexNet, right?
AlexNet was one of the models. We ran all the models,
In that comparison, what did you compare? Like, was it accuracy or was it throughput?
Our goal was to look at throughput, but if you see this chart, we also accuracy
like
is
the next one.
I'm sorry, this one.
Next one. Yeah, this one. Yeah.
Right. This was more to see the impact of batch size rather than the accuracy. Accuracy is generally stable at these values that you can see on the screen. So these are pre-trained models. So we used pre-trained models. We did not train these models. We are using pre-trained version of this model available for all the frameworks. So accuracy wasn't a concern. Throughput was more of our concern.
I see. So in terms of the accuracy, there's no difference regardless we are using any of them, right?
Yes, and accuracy doesn't really change with increasing batch size, if that's what you're referring to.
Not batch size, the MXNet or PyTorch like that.
Right. So they are the same architecture. All of them have been trained on the same data set, ImageNet.
Okay.
So there's no difference in accuracy.
Okay. Thank you.
Right. Thank you. Any more
So
questions?
I also have a question, actually more, it is more a curiosity. So in one of your initial slide, you mentioned the configuration files used to run the experiments. And one thing that attracted my attention is the number of word maps. What are the word maps?
So if that's a good question. So I think I did not explain that. So whenever we benchmark any sort of systems, or whenever we talk about benchmarking, there are some initial runs that we need to discard, because that is the phase where the system is warming up, as we call it. That means it's loading up. Sorry, that means we're loading up the we're linking all the libraries, we are firing up all the modules and getting the system ready. We are just preparing the system. So first few inferences, we tend to ignore it, because those are generally the warm-up phase of the runs. After those warm-up runs are done, then we start getting stable results, and then that's what we use for our as results, actual results. So I hope that answers your question.
Yes, fully.
Okay.
Thank you very much. It was very clear. So it's just an experimental setup methodology.
That's true. Yeah.
Okay. So thank you very much. I think that we are done with our technical session.